I imagine tired. I'm sorry. I am interfering, or I'm the what is left between now and dinner. But hopefully we can have 1 hour and a half of. I mean, hopefully it's enjoyable, and then we all can go for a very delicious dinner. So what I'm going to do is we were discussing about understanding collisions in the clock. So we discussed that in the clock, in principle, there are P wave and S wave interactions. In this case, what I started to discuss is the case when I have nuclear spin polarized atoms, all the atoms in the same minus 9.5 level, for example. And the spin, effective spin degrees of freedom, what we discussed was the ground and the excited state, the orbital degree of freedom. And we started discussing the many-body Hamiltonian by using different type of simplifications because the interactions are weak. We mapped the dynamics to a spin model that we were able to solve analytically, and with that we were able to compute what is called the density shift, or how the ticking of the clock, how the tuning of the clock depends on the number of particles. And we got this very simple expression that is, of course, depending of the number of particles, but also linear depending on the excitation fraction. I mean, cos theta is associated with SC, the magnetization. So it's set by the first Ramsey pulse. But besides that, I mean, this very simple model, mean field model, allows us to actually reproduce very well the experimental observations of the density shift. So that was a big win. And by understanding that, we were able to operate the clock in a regime where interactions were not important and improve the accuracy and the sensitivity of the clock. So that was where we ended. Remember, when we were measuring Ramsey spectroscopy, we were measuring basically expectation value of total S minus. That's what is measured. I mean, we apply a second pulse in order to map the phase to population, but basically the measurement of the Ramsey spectroscopy is expectation value of S minus. An expectation value of S minus, it can be a complex number, and therefore have two parameters, the amplitude and the phase. So the amplitude is how large are the amplitude of the oscillations of the Ramsey fringe, and of course the phase is associated with how much rotation happens as a function of time, and it's telling me information of the detuning. So far we were looking at the density shift, the phase, and we were able to reproduce it very well. Now the experiment can also measure the contrast of the oscillation. So you have a Ramsey fringe as a function of the dark time, and you have a Ramsey fringe that, for example, can decay as a function of time, and you can measure the amplitude of this oscillation that is associated with the magnitude of S minus. This is called many times contrast of your Ramsey fringe. And in the experiment, what they saw is that this contrast of the oscillation unfortunately decay. That's very bad because, of course, it limits the time that you can do your measurements, and very not ideal for clocks. So let's look a little bit at the amplitude. So they saw a decay of this oscillation, and well, the first thing that we try to do is understand if this decay could be understood at the mean field level. Remember, at the mean field level, I have a Hamiltonian. I was modeling my Hamiltonian. I chi SC squared plus, well, they have some term that is proportional to SC. Remember, that's how we were deriving the interactions in the clock. And at the mean field level, I was approximating this term as 2 times expectation value of SC, like factorization. I'm factorizing the term and assuming that there is a constant magnetic field, because SC, the population in principle, is commutes with the Hamiltonian. So you see that the population is, the SC is conserved during the dynamics and only set by the initial pulse, by the pulse before the Ramsey fringe. So remember, we are doing a Ramsey experiment when we first do a pulse theta, and then during that time we turn off the laser and just let the system accumulate a phase. And in this case, well, of course, it's affected by the interactions. So at the mean field level, we set this to be a constant, and therefore the expectation value of S minus as a function of the dark time is just the expectation value at 0 time. I mean, that is associated with the first pulse. And then, besides the detuning that is trivial, of course, I want to have something that is proportional to the detuning. But then I had an extra term from the interactions that is this delta detuning that I also is linear in time, and this delta and have Cn C. But this it is something that I'm going to replace this delta by this delta by something that is proportional to chi expectation value of C plus Cn. That's the delta chi. But this is just a constant, and therefore, in principle, the oscillations should not decay because this is just a phase. So why the oscillations decay? I mean, at the mean field they should not decay. The reason that they can decay is because actually, in the experiment we have a one-dimensional optical lattice, and we don't have a single pancake. So this n, the n that goes here, or this density shift SC, that is, remember that expectation value of SC is proportional to minus n half cos theta. So this can change from one pancake to the other. I don't have something that tells me the distribution is fixed between pancakes. And so there are pancakes that are going to have at the center of when I have pancakes that I have a lot of atoms, then of course the oscillations are faster. Whereas the atoms that are at the edges, the oscillations are slower, and therefore I have a phase that is changing across my sample. And therefore, that is going to introduce some dephasing because if I have a bunch of systems, each oscillating with different phase, my sample is going to dephase and decay the contrast. So that's what we try to analyze. There is also some component of not ideal, actually inelastic losses because atoms in the exact state unfortunately collide and are lost from the trap, but these were just a small ingredient. It was not the leading mechanism. So let's try to analyze a little bit what is the mean field predicting when I take into account that the Poissonian distribution of atoms in the lattice, yes? So look, and this is the solid lines or the dashed lines are the ones that the theory predicts. The solid lines are the experimental points. This is contrast or amplitude versus time in milliseconds. So you can see that for very small tipping angles, where the density shift is the largest, and therefore when the phase is going to change a lot because I have a large density shift, then the contrast decay very quickly, and then and then actually the contrast and this simple mean field model reproduces the experiment very well. That's great. But now, as we start to progressively increase the tipping angle, so if you can see, I'm going to show different initial tipping angles. And for example, if I go here at the case when there is no density shift, there is no phase. So at the point of the crossing, I have a very bad deviation between what the experiment sees and the theory. The theory, for example, predicts, the mean field theory predicts something that is almost doesn't decay. And well, similar effects, but this also I have is also decaying very bad, disagreeing badly. So we were surprised. Why is that?
So how come it can increase? I mean, the series seems to increase at low time.
Here, yes, these contrasts also include a little bit of particle loss. And so it's a combination of both of them. So that's why.
Okay, there's just some stuff that you haven't explained.
I added in the contrast, but it's just pure mean field. That's what I want to emphasize. We have a bunch of pancakes that are actually decaying because they have different phases across the lattice and some extra loss that happens as a function of time. So what is going on here? Why is that deviation if the mean field shift was so nice? I mean, the mean field shift was agreeing very well. So this is where we realized that actually the experiment was sensitive enough that it one started to see the role of quantum fluctuations. That means this approximation of approximating SC squared by this term is not valid. So I'm going to introduce failure of mean field theory, what is going on. So I think what we understood is that the problem is that if I have a bunch of spin 1/2 particles and they are getting entangled, then what happens is that if imagine that I have a change of atoms. This is a bunch of spins, yes? N spins, for example. When I measure expectation value of a single particle operator, this is the sum of the measurement of individual spins. It's sum over I, but it's one body observable. That it means when I measure, for example, expectation value of sigma x1, what I'm doing is this, I'm tracing over one atom, one part, I'm tracing over this atom and ignoring the rest, yes? That's what I'm doing. So the point is that if the system is a product state where this atom is not correlating with any other, if this atom is just a product state, if my density matrix is something that is a product of a single particle density matrix, if I measure one, I'm not going to affect what is the role of the others. I mean, I'm just tracing one, I don't lose any information, and therefore, if I compute the trace of rho sigma 1x is just going to be associated with exactly what one part happens with a single particle and not with the rest. So it's not going to, this contrast should not decay because it's one spin that is precessing, so it should not decay. And this is the idea of the mean field theory, that the contrast, if I measure, except from the different average that I'm doing, it should not decay. On the other hand, if I have an entangled state, I have a state that there is entangled, this particle has correlations with the rest of the ensemble. Whenever I trace over one particle, then I'm going to lose the information. I'm cutting some information when I measure that. And therefore, it can have that, I can try to lose the information and introduce some contrast decay. So I don't know if you are familiar with the idea of Rayleigh entropy, but somehow when in quantum information, for example, the idea of if I have a density matrix of a pure system, for example, and I try to measure trace of rho squared, because it's a pure system, this has to be always 1. Of course, trace of rho is always 1, but trace of rho squared is also 1 if I have a pure system. On the other hand, if I have defined a subsystem, for example, subsystem A, this is my single spin, by tracing over all the other spins in the B, that is the rest of the example. And if I have a system that is entangled, trace of rho I squared can be smaller than 1 because I'm losing information. So it happens that for as small, as simple as the one that I have, chi SC squared, you can show that because the expectation value of SC, for example, I'm going to give you an example of when theta is equal to pi half. That means I prepare a system on the equator, yes? So trace expectation value of SC is going to be 0. Expectation value of SY is going to be 0 for symmetry. And the other, not only non-trivial expectation value of is SX. This is different from 0. So you can show that in principle, if I look at the trace and my subsystem A is just a single spin, only one spin. So I'm going to trace, my A is a single spin and the rest is the other part. You can show that actually trace of rho 1 of my individual spin square is associated with expectation, with the contrast, with the expectation value of Sx. So the decay of the contrast is connected with the fact that I'm developing entanglement in my system. Of course, I have, there is a lot of other losses in the system. In my case, there are collisions happening. So it's, I cannot say that it's necessarily completely entanglement, and we could not say that. But nevertheless, we can try to account for the development of correlations and see if we can reproduce the dynamics. Mm-hmm. And what we did is a very simple treatment of the quantum noise that I have found that is very, very useful for trying to include correlations. I mean, of course, if we are going to solve, this Hamiltonian is simple enough that I can solve the Hamiltonian numerically exactly. It's a very simple Hamiltonian. But there are many cases where the Hamiltonian is not as simple as this, and still I want to account for the effect of quantum correlations. So one method that we have used and is very, very useful is called a truncated Wigner approximation. And I don't want to scare you with the name, but I'm going to give you a very intuitive picture of what is happening. So it's called and I have some reference here. It's called truncated Wigner approximation. And I'm going to give you a very simple example of how to do it. So if you have a spin pointing along the x direction, you know the expectation value of Sx is n-half. The expectation value of Sy and Sc is 0, yes? But you also know, because of the Heisenberg uncertainty relation, that the expectation value of the standard deviation is not 0, but is proportional to n divided by 4. And this state is this state that is just a product state. It's not a correlated state. Nevertheless, if I'm going to solve a mean field equation, yes, sometimes what I can do, I mean, the fact that, for example, I'm doing an approximating the Hamiltonian, and giving this example, this is the mean field solution. With this example, and Sc is a constant of motion, I can solve for the mean field dynamics, and I said, as I said before, that the dynamics as a function of time is this at time equal to 0, e to the I or minus I 2 chi expectation value of Sc times time. This is a constant. So this is my simple mean field dynamics. Yes, it's of a particle experiencing a magnetic field. How can I include the effect of quantum correlation of the initial state, the quantum noise that is not trivial? Well, I notice that actually Sx at time equal to 0 is not a fixed number. It has a variance. Yes? And the variance it has is kind of a Gaussian distribution with a width of this form. So the simplest way that I can account for quantum correlation is saying, well, my expectation value of Sx is not actually replacing Sc by the expectation value, but I'm going to average over the initial noise. Yes? And the initial noise, for example, is going to be accounted for a distribution, something W, that depends on Sc of 0, Sy of 0, and Sc of 0, Sx of 0, Sy of 0, and Sc of 0, that has the following properties. Along the, for example, along the, imagine for simplicity, along the x direction, there is no noise, too much noise. I mean, the system is pointing along the x direction. So to an excellent approximation, the x component is almost in half. This is a delta function. But along the y and the z directions, I can approximate it by a Gaussian. Yes? And a Gaussian has a distribution that is going to be proportional to, for example, Sy 0 with the mean, with the variance, and the variance is n divided by 4, and then I divided by 2, so it's 2. So I have a variance, a Gaussian variable that has, or maybe I can put, this is the sigma square and then divided by 2. and with the proper normalization of the variable. Yes. Same thing I can do for the z direction. It's the same Gaussian. Yes. So what I do to compute the expectation value of S minus, including the quantum noise, is going to S minus, the expectation value of S minus, is try to weight the mean field behavior. This is the mean field behavior. But I weight and integrate over the distribution of SC0, SY0, SX0, DSC0, DSY0, DSC0, this XC0. So I basically weight my mean field solution with a distribution that accounts for the initial noise. And it's very simple to do a Gaussian integral. Yes, in this case, it's just an integral over a Gaussian. And I can get an analytic expression, for example, for this case. For example, if I have a Hamiltonian like this, then I can get where, for example, C is equal to 0, the mean is 0. Yes, and if I have pointing along the x direction, then at the mean field level, I would get no evolution because the expectation value of C is 0, so I don't get anything. But if I do this trick, and instead of consider C the mean value, I do the integral over this quantum noise at time equal to 0, you can show that S minus actually is going to decay. So in this case, when I do the Gaussian integral of this quantity, it's going to decay as minus chi squared t squared n divided by 2. It's decaying. It's not, at mean field level, I have something that is fixed. But when I include the noise from the quantum noise at time equal to 0, then I get something that decays. And this is what was happening in the experiment. So in the case remember that the worst case, when the density shift was completely 0, because I didn't have anything that will going to introduce any decay. But when I included the quantum noise, then I can account for this quantum noise in the initial conditions. And just by doing this very simple treatment, we were able to reproduce the experimental observations very well. So this is a lesson that we learned, that sometimes even though solving a quantum problem is very hard, there are tricks that you can do by accounting the noise the quantum noise in a very simple way that you can tackle the quantum problem. And I recommend a lot, if you really want to know this technique, it's very useful for trying to have an answer of how quantum fluctuations will modify the experiment. So in this case, we concluded that not only we have the appropriate model, but moreover, quantum correlations were important in the system. So that's the lesson that we learned, and it was a very nice win-win. We were able to improve the precision of the clock on one hand. On the second, we learned about the many-body properties of the collisions of these atoms, and then we can learn that even though they can be very complicated, very simple models can be used to determine the behavior. Any questions about this part? Mm-hmm. What is truncated Wigner approximation? Because I'm only including this is the distribution that I'm writing here is called the Wigner function. It's associated with the Wigner function in spin. It's truncated because I'm assuming that the noise, the truncated Wigner, is fixed in time. Yes, I'm only including the noise at time equal to 0. If I were going to do the exact solution, I will have to account for the development of the noise as a function of time. And people sometimes have been able to do that by adding random stochastic terms during the dynamics. But the problem is sometimes the Wigner function is not it's a positive definite function, so when you try to add this noise, it's not that simple and not necessarily you improve what is happening. That's what is truncated, but anyway, in many cases, it's enough to seed the initial distribution and gain a lot of information about the dynamics of a quantum system. Now in my group, we use truncated with an approximation for everything, and we are able to reproduce dynamics of dipolar particles, dynamics of alkaline atoms, dynamics even of fermionic particles. There is a way that we can adapt the truncated Wigner even for fermions. So it's a very nice trick to account to leading order of what happens from quantum correlations.
From your description of the dephasing from different precession times and different pancakes, I was wondering whether it might be possible to see some sort of revival if you wait long enough.
Well, in the experiment, the problem is that there is EE losses, unfortunately. So in principle, that's correct. The mean field solution should revive at some point, in principle, but because they could not wait, after these times, then there were other systematics in the experiment that were killing, yes. But in principle, yes.
Why do you choose for a Gaussian distribution if you're...
What is Gaussian?
Just the law of large numbers? Or
Yes. So what is Gaussian? I can tell you a little bit more. Just one thing. So you know that if you have, what you should do, or what we do, is that we have a bunch of spin 1/2 particles, yes? So in principle, if you have a spin 1/2 particles, you know that the expectation value of Sx is 1, and the expectation value of sigma y is 0, and sigma c is 0. But when you compute the expectation value of sigma x squared, this is 1, because Pauli matrices always give you 1. And expectation value of sigma y squared is equal to 1, 2. So what you do, if you are really try to reproduce what is happening in the system, instead of sampling a Gaussian distribution, you have to sample a discrete distribution that has values plus minus 1. So if omega, the distribution of the c and the y components are just a bunch of random variables with plus or minus 1, you are correctly accounting for all the distributions at time equal to 0 of the spin. But if you compute, because of the central limit theorem, and you have large number of particles, you can show that this approximates to this distribution. So yeah. But sometimes, if you, for example, this quantum system has a revival, and if you want to account for the revival, you have to sample that way, not with the Gaussian, because the Gaussian assumes something that is continuous and removes the granularity of your spin system. But in this case, because they went only for very short times, we didn't need to take into account the granularity of the spin system.
So is there a way to improve the contrast?
Is there
A way to improve the contrast?
the improved in contrast? Well, no. Unfortunately, well, if you do, one way to do it is trying to do a time reversal of the Hamiltonian. For example, these are some people in cavity systems that have this type of Hamiltonian chi SE squared. You can try to do something like this, because you might think, can I do an spin echo that removes the dephasing and keeps the contrast? Unfortunately, this is a quadratic Hamiltonian, and a spin echo doesn't work. But if you do a many body echo, for example, that you change the sign of chi, you can improve the contrast decay. The contrast decay is not bad, though. The contrast decay is telling you that the system getting entangled. And in principle, if you have no other sources of decoherence, you could show that if the system were perfect at a longer time, you will form a cat state that could be very useful for metrology. But so not necessarily contrast decay is bad. You will have to measure something else, not just a Ramsey protocol. All right. So this is my conclusion for this first part, that I just doing nuclear spins that are spin polarized, that even in this very trivial system, we get some information about the many-body dynamics. Now I'm going to add one extra complexity, that is, instead of working with a nuclear spin polarized state, I'm going to start to explore the nuclear degrees of freedom and try to explore this SUN symmetry that I mentioned, but we have not explored. So, okay, so yes, so I'm going to now try to use a combination of both a spin and orbital degree of freedom. So the Hamiltonian is going to look very complicated, but I'm going to write it to you because it's important to see, even if in the SUN symmetric case that we have a single scattering length or a single scattering volume per channel, then it still is complicated, but I think it's important for you to look at this. These are still only, I'm going to just stick with the interactions. So imagine that I'm going to have a system that is ultra cold, where p-wave interactions do not matter. So I'm just here restricting to S-wave interactions. The S-wave interactions, I can have collisions between atoms in the ground state. But now that I can have two different nuclear spins, m and m prime. And for example, when you look at this Hamiltonian, for fermions in general, what you write is something in phi daga up, phi up. This is the density of up, phi daga down, phi down. Maybe you are used to this type of interactions for fermions. This is exactly the same. I just put in normal order because this can go here, and this is the density of number of particles in spin m, and this other term is the number of atoms in spin m prime. Yes, so it's a density-density interaction for the ground particles. But now I can have different, m is the different number of spins, nuclear spins. Same thing for the excited state, but just different scattering parameter. But now I can have two terms. I can have what is called direct and the exchange term, and maybe these terms are familiar from the helium atom. The direct terms are again density terms, so you can put this here, going here, and it's the number of atoms in ground state atoms with the spin m, and the number of atoms in the excited state with the spin m prime. It's a density interaction, and you can show that the term that goes to here is the sum of the two scattering lengths, Ag plus and Ag minus. This is one term. And then there is another term that is called the exchange term. And this exchange term is going to be proportional to the difference between these two interaction parameters, is the difference. And what it happens is that it's going to introduce flip-flops. That means you can see that this Hamiltonian tells me if I have, for example, an atom in the excited state with a spin n-half, an atom in the ground state with a spin 7/2. Because of this term, what happens is they are going to switch the position as a function of time. They are going to flip-flop. This is other way to say that triplet and singlets are the good eigenstates, not up and down. Yes, that's why they flip-flop. So what the first task that I'm going to do is trying to understand this type of physics, and these were done in very beautiful experiments in Emanuel's Brock group. So I'm going to summarize them. There is the simplest case that they deal. I'm going to tell you that if you are going to deal with the strontium and the temperature is not 0, you are going to have the same type of interactions, but you replace the S-wave pseudopotential for the P-wave pseudopotential, exactly the same terms, except that you can see I'm going to have my gradients there as I had before. So this is the many-body Hamiltonian that describes the full system, the sum of the S-wave and the P-wave. All right, but let's try to understand a simple example first. These were experiments done both in Trento, by Leonardo Falani, and also done in Emanuel's block group at that time in Mainz, yes, in Mainz still. So the idea is that they have atoms in a 3D optical lattice, and they were able to actually put 2 atoms per lattice side. And then they select, this is the work done with ytterbium, and they select to populate only 2 nuclear spins. Remember that we have SUN interactions, so if I populate these 2, I will never scatter 2 other 2. And if you look at the Hamiltonian that rules the behavior of 2 particles in a lattice side, in this case, they were able to prepare the particles, of course, in the ground state of the lattice. So only S-wave interactions are going to be possible because the wave function is fully symmetric. So I have 2 particles, and actually what happens in alkaline atoms is because for the same reason that in the clock we can drive the transition, the G factor for the ground and the excited state is slightly different. So in the presence of a magnetic field, there is going to be an energy splitting, the energy splitting between 5/2 E and G is slightly different between 3/2 E and G. They just apply a magnetic field. So if we go back and remember what I was writing before, for two particles, now I have to conserve the number of particles in E, and I have to conserve the number of particles in the ground state. So the only two accessible states are the triplet in EG, but of course multiplied by the singlet in the nuclear spin. I'm going to call up 5/2 and down 3/2. And then the minus state, that is going to be the singlet and of course the triplet, to guarantee that the wave function is antisymmetric. And these two states are associated with the plus, give me the EG plus, and the minus give me the EG minus scattering length. So it's a very simple matrix. This is the plus, this is the minus state. So I call U just the, let's see, where I thought I was, I have it there. Yes, here. U, EG is proportional to the scattering length times this, times to the wave function overlap of the Wagner orbitals, Wagner state in the lowest lattice side. But well, the important part is that it's proportional to this term. But now look that the magnetic field, the magnetic field favors instead of up, down, down, up. The magnetic field doesn't want singlet or triplets, and therefore the magnetic field is trying to couple these two states. You can see that the eigenstates of, if the magnetic field is very large, the eigenstates are superpositions of up and down. And in fact, if the magnetic field is really large, for example, the states that are eigenstate of the system are going to be E down, G up. This state is just the difference between plus or minus, for example. Yes? Or you can also have E up or G down. So these are the possible states. Here, in this case, for example, this is an eigenstate of the magnetic field. The magnetic field that is uncorrelated state. All right. So the idea is that if I have the Hamiltonian, and for example, imagine for simplicity, I put this magnetic field equal to 0, because I have a superposition of these two states, and each one is going to acquire a different phase because they have different interactions. That the system is going to evolve. The population, for example, of this state, the population of the ground state in up, is going to oscillate with a rate that is proportional to the different energy between the two particles. So it's just, and if you imagine a spin 1/2 particle system, this is kind of the matrix element sigma x, and this is sigma c, kind of. So if you look at the time evolution, you can see that the dynamics is going, the population in the state up is going to oscillate at a rate that is set by the exchange interactions. And I encourage you to solve, this is a 2x2 Hamiltonian. So just as a homework, I'm giving you a lot of homework, but if you want to, you can show that the dynamics should be oscillations of the population. If you prepare this initial state and you let it evolve as a function of time, what you should see, if you measure the population of the atoms in the ground state, you measure this state, for example, the population of this, you are going to see this oscillation. And in fact, that's what they observe in the experiment as a function of time. They observe very nice oscillations. Yeah, well, there is some decay, but by trying to look at the frequency of those oscillations, they could determine what is this B exchange term, the difference between EG plus and EG minus. So that's good, that's great. The oscillation, the system was decaying, and there is a problem that actually in ytterbium, this is where I realized that there were not only losses in the EE collisions, but they were also losses in the EG collisions. Unfortunately, in ytterbium, there are extra losses. And these extra losses, they were attributed to the fact that, okay, they were extra. First, they saw losses. The population was not constant. The second is that if you think about the percentage, you see that the percentage is only 6%, very tiny, very tiny. They were having problems in trying to prepare this initial state. This initial state, they were having issues. What they realized is that after some different measurements, is that for the magnetic field that they were using, the EG plus scattering length was enormous. It was on the order of 3,000 volts, where the scattering length for the EG minus was much more moderate, 219, approximately what they expected to have. And this behavior of these very different scattering lengths between the plus and the minus, then later was pointed out that this is the presence of what is called an orbital fetchback resonance. So I think Soren, my understanding is that he was going to explain you a little bit of fetchback resonance. But the basic idea of a fetchback resonance, if you have an open channel that is particle atoms, independent atoms colliding, and a closed channel that is the molecular channel, and when these two channels cross, at this point there is a new bound state that comes into the problem, and when you have a new bound state, the scattering length diverges. So by controlling the splitting between the closed and the open channel, that can be done, for example, in alkali atoms by a magnetic field, because the ground and the closed and the open channel have different magnetic moments. They are able to tune the case, and at some point the closed and the open channel are resonant, and at this point is when you have very strong scattering length. So the scattering length diverges at this point. So in this case, the open and the closed channel were actually this plus and the minus state. And they discovered that actually there is a very similar phenomenon as a fetchback resonance. They call it an orbital fetchback resonance. And this is the explanation not only of the losses that they were seeing, but the reason why these have the huge scattering length for EG plus. So because the scattering length for EG plus is so large, it means that they will never have a ground state that has the singlet in the nuclear spins. I mean, it's so large that this is going to be always an excited state. We are trying to prepare a ground state of the system of a single two atoms in the well, because the scattering length for the EG plus is so large. Then that means that the eigenstate, the lowest energy state, is always going to be the triplet in the nuclear spins. And later in my talk, when I'm going to tell you about Kondo model, then that means that this system will never realize the Kondo model, because the Kondo model wants to have a singlet as the ground state. I can tell you something that it was funny when we were trying to work with them out what they were seeing, is that they have a sign confused. And I'm going to tell you this story briefly. So the idea is that the reason why they have the sign confused initially is because, for example, they started, I think, with to try to prepare 1/2 and -1/2. So that among all these different nuclear spins. Yes? And what happens if you look at the Clebsch-Gordon coefficient of the transition, the Clebsch-Gordon coefficient of this transition is positive, and this Clebsch-Gordon coefficient of this transition is negative. So that means that if, in general, the way that they start the experiment is to have two atoms in the ground state. Two atoms in the ground state, and therefore, by Pauli exclusion principle, because they have GG, the only way that they can exist is that if you start in the singlet nuclear spin state, yes, because of the Pauli exclusion principle. So what they wanted to do was to try to add a laser drive. I mean, this is where here that and GG. They were trying to add a laser that transformed this state into EG plus GE and keep the nuclear spin the same. Yes, but the point is that because they have different Clebsch-Gordon coefficient, this is inverted and this gets plus and this gets minus. So at the beginning in the paper, they thought because of that. If you see what the first paper, they thought that they had this sign wrong the other way, and they were saying, oh, we will be able to see Kondo physics in this problem. But then they realized that actually you have to be very careful with the Clebsch-Gordan coefficient, and it's no other way around. So nowadays, we know that the only atom that is, has this sign reverse is actually ytterbium 171. And maybe in principle, ytterbium 171 could be the type of isotope that will allow us to have a problem, simulate something as about Kondo physics, where the lowest energy state is the singlet. But with that, I mean, at the least they understand this, they understood this very simple problem of the exchange interactions for two atoms. Any questions about this?
Regarding this magnetic field, so do I assume I could find coupling? So because you have the magnetic field.
That's an excellent question. So it's true that the reason why the ground here is 1 is 0, and the excited state is 3 p 0. So it's true that if they were really j equal to 0 states, the g factor should not change and will have exactly the same g factor. So the way that I'm drawing here, in a presence of a magnetic field, this is if you have two nuclear spins, then the g factor that is computing the energy difference between in the presence of a magnetic field should be identical. But remember that there is a nuclear spins, and that's why I allow to drive the transition. So this tiny admixture of that allow me to drive the clock and give this very a finite lifetime and allow me to excite, changes the G factor by 60%. So the fact that there is nuclear spin is the reason why there is this energy mismatch in the G factor of the ground and excited state. And this is very good because June used this to resolve different transition in the clock. Yes, if you have a bunch of levels, I mean the ground state has almost no effect, and if you have something that changes, then you can add a laser that have this frequency instead of this frequency, and you can resolve the transition. And that's one of the ways that he has played with that. All right, so now let me go to the other experiment that we did. That is, now we're going to drive our clock, same thing that we did before, but we're going to add color. And we are going to have a clock that is now where we have not only the clock state that we want to interrogate, but in addition, in the 1D lattice, we allow a mixture of spectator atoms. It's not that Jung wants to operate the clock that way, but it's just a way to try to understand the SUN physics that we wanted, try to probe that there is in fact SUN interactions and SUN collisions in the clock. All right, so again, we are going to do a simplified model. Still, the interactions are very weak. We are going to write an spin model, and this spin model is going to allow me to simplify the physics. So let me tell you what is, in very simple terms, what we did. Okay, so remember that before, when you have nuclear spin polarized atoms, we grow the Hamiltonian that, and this is the homework problem that I want you to solve. And I'm going to change, because now I have nuclear spins and orbital degrees of freedom, I'm going to write as T as the operator that acts in the EG degrees of freedom, in the orbital degrees of freedom. So the Hamiltonian that I wrote was something like J perp Tn1 dot Tn2. There was a term that was the exchange term. There was a term that was chi, that is proportional to Tn1c Tn2C. And then there was a C term that was proportional to Tc1 plus Tc2. I mean, maybe I'm changing the order. Sorry. That's N1, N2, Cc divided by 2 plus a constant, some constant that I call it K. This was the case when I have spin polarized atoms, nuclear spin polarized atoms that we discussed before. Then, on the other hand, if I have, instead of spin polarized atoms, I have atoms in the singlet state. What happens is that, for example, this B term, remember that I wrote it like BEG plus minus UEG minus. If you look at my notes, there is P wave interactions and then S wave interactions, and this chi term was proportional to BGG plus BEE minus 2 BEG plus, and this C was proportional to BE minus BGG. Everything was normalized by 2. What happens if I change from triplet to singlet? I have almost the same Hamiltonian, but the only difference is that the S wave interaction becomes P wave. Yes? So basically, when I have the triplet, the singlet here, I have something that is, let me put this J plus. Let me call everything this plus and this plus. And now if I have the singlet, then I have this pair, but let me call it minus. And I have the same form of the operators. The only difference is that, for example, this J pair is going to be, instead, it's going to be UEG plus minus BEG minus. Because instead of having S wave, I have P wave and vice versa. Then this term chi, I'm going to be also chi minus TC, N1 and N2. But then instead of having this chi, is going to be proportional to the S wave interactions, UGG plus UEE minus times UEG plus. Yes, S wave. And similar for this term here, then I'm going to have a C minus term that I'm going to have TCN1 plus TCN2 divided by 2. That's the only, everything is the same except that now C is UEE minus UGG divided by 2. So the way that I can write the Hamiltonian is that, what I'm saying is that if I have up, I have this Hamiltonian. If I have triplet, singlet, I have this Hamiltonian. So one way to write it is going to be, for example, if I have SU2, I'm going to write it S dot S minus 3/4. Plus 3/4, sorry. Because if I have up, this gives me 1. If I have a singlet, this gives me minus 3/4, that gives me 0. So this is a projector on the triplets. And then this Hamiltonian, the other case, I'm going to multiply instead as a projector on the triplets. Yes, if I have a triplet, is 1/4. This cancels, and if I have a singlet, I'm going to have, if I put a minus sign here, I have 1. So it's a projector into the singlet and to the triplet. For SUN, I can do the same thing, but I can write generic projectors in SUN. So instead of having this Hamiltonian, I can try, the analog of the projector of the triplet or the singlet for SUN systems, the projector on the symmetric is just 1 plus sum over Mn Sm Snm for my two atoms, atom 1 and atom 2. divided by 2. And for the projection of the antisymmetric state, is going to be the same 1, but I have a minus sign here. It's the same thing. I mean, Nm, Mn of the 2 atoms. Mn, Nm. Why? This Hamiltonian, what it does is swaps if I have a state Mn, when I add to this Hamiltonian, it makes me this, it transforms it in Nm. It's a swap operator. It swaps the spins. Yes, that's what this term does. So you can see if I have something that is fully symmetric, when it swaps, then I get 1. But if it's antisymmetric, because I have a minus sign, when I swap, it gives me 0. Yes? And similar for this term. If I have an antisymmetric term because of the minus sign, when I swap, it gives me 1. But if I have something symmetric, when I swap, it gives me 0. So another way to write the projectors in SUN here is to write something like this. It's going to write this 1 plus this SS term divided by 2. I mean, I'm sum in N and M, and 1 minus SMN divided by 2. I'm swapping, this is the projector on the symmetric, this is the projector on this antisymmetric. So my full Hamiltonian is the sum of this term plus the Hamiltonian of this term plus this term. Yes, maybe I'm going to put it in colors. Is the sum of these 2 terms. This term here plus this other term here. Okay. So what we did in the clock? So this is the Hamiltonian that describes my SUN system, the sum over the 2. What we did in the clock was trying to see what is the density shift that the clock have when I have a bunch of spectator atoms. And very naively, what Jung did is to say, well, if I have SUN interactions, then the density shift is going to be the density shift between these 2 atoms that only have p-wave interactions, and the density shift coming from the interaction between these with the rest. So the first term is the term that we already understood for a nuclear spin polarized sample. That is what we measured before. That is the linear slope. And then if you write this very simple model, so it's the sum of this term and this term, these 2 terms. And if you do this, and now you have a mixture of nuclear spins, there is no spin coherence, a mixture of nuclear spins, with this very simple model, you can show that the S-wave interactions, that is the interaction between the SUN interactions, that is the interaction between these atoms and these atoms, because of the property that this is independent of the nuclear spin, just depends if you have a singlet or triplet, and that's it. Then what happens is that no matter how you distribute your atoms, as long as you keep the same number of spectator atoms, but redistribute or shuffle them at will, then you should see the same thing, because I don't care how many atoms are in this nuclear spin or this nuclear spin in the nuclear spin. I don't care. I just care that I have the same total number of atoms because the interactions are SUN. So that was the experiment. Jung changed the distribution of these spectator atoms, and actually you can show that the density shift coming from these spectator atoms is just related by a quantity that determines the number of spectator atoms times some scattering length or some interaction parameter that is going to be a superposition of all these different parameters here, but it's fixed. So it's going to be associated with this that we could calculate a superposition of this. But the important part is that it doesn't only involve the number of spectator atoms. That's it. And that was the theory prediction, that if you have SUN interactions, it should be that way. And this is what they saw in Ramsey spectroscopy. So what they did is that first, this is the density shift, or the changing in the ticking as a function of the excitation fraction if all my atoms are in this nuclear spin, the same nuclear spin. This is the straight line that they measured before. Same thing before. Now what they did is that instead of and this is the transition they interrogate. They interrogate the same transition, but having only 29% atoms in this, and the other atoms were populated with other nuclear spins. Another experiment where they interrogate this component, and you have a very different component on the others. And there is another experiment where they interrogated this with 12% and another contribution of this other. So what they saw? They saw that all of them have the same slope, the same slope because this is just the p-wave interactions. Because, I mean, here we are normalized by the same, assuming that you have 4,000 atoms in each of the interrogated components. You normalize the shift so that you have the same number of atoms of interrogated atoms. But because you are changing the distribution of the other atoms, so here all the atoms are here. Here I have more other atoms in the other states, and here I have more atoms in the other states. So they saw that the density shift was, have the zero crossing, but this shift only depends on the number of spectator atoms as I was predicting in the theory. So for example, you have 12% you have, in this case, you have 88% of interrogated atoms. They have much larger shift because there is larger population. And that's what they saw. And it doesn't matter if they interrogate this or they interrogate this, they actually have the same density shift. So that was a way that we show that there was SUN symmetry, and the model, all these theoretical lines were consistent with this model that I show you. And moreover, they show that the slope for all these cases actually was fixed because the slope was only determined by chi, this quantity chi that depends on the interaction parameter that was independent of the temperature. So just to summarize, we have this experiment that introduces a little bit more complication, but it's still a simple model in terms of nuclear of this Hamiltonian was able to reproduce what they saw. All right, so.
It seems like on this graph at least that the shift that you have on the p wave and the shift we had before is of the same order as a new shift. You know, it's a shift from 0.
Yes, so this is slope.
But this slope is from what we expected.
Before.
It's a p wave.
Yes.
But then the other is the same order of magnitude more or less, right?
Yes, because S-wave interactions are stronger.
Yeah, but my question is, why is it so that, I would expect that S would be so much stronger that they would be enormously large shift, and this is not the case.
Well, in some sense, for the temperature that they operate,
the P wave are as strong as
the P wave is because the P wave is still proportional to the kinetic energy. They are not, if they would reduce the temperature, 1 microkelvin, between 1 and 5 microkelvin. So if they would have reduced the temperature to nanokelvins, and this is what we will see now, the P wave will be fully suppressed, and all what you have is S wave. But for the S wave, for the temperature, it was not the case. So still the P wave and the S wave are kind of the same order. So yes, so that's the complication of the clock, and that's why Jun is moving to another experiment where really he can reduce the temperature to quantum degeneracy. That's how the new clocks operate. So the point is that this, as I said here, this density this density shift allows us to set the P wave interaction parameters, and with this new density shift we could determine the S wave interaction parameters. This quantity depends also on the S wave interaction parameters. So by matching the theory with the experiment, we were able to extract all, we were able to extract all the scattering parameters of strontium-87. This with the help of Paul Julien. That Paul Julien is the expert on collisions, and he told us that actually there is a one-to-one relationship between the, Jesus. There is a one relationship between the S wave, A is the S wave, B is the P wave, and there is a universal relation between S wave and P wave in terms of the C6 coefficient. We didn't know that, but with his help, we were able to use the relation and try to connect S wave to P wave on one hand, and second, we were able to determine not only the elastic but the inelastic terms for the EE collisions. And with that, from these density shift measurements, we were able to extract all the different scattering parameters for strontium, all of them. That was a remarkable task. Of course, it was a little bit concerning to publish this because, I mean, still it's a very simple model what we are doing, and we didn't know exactly if it's going to, if the theory was completely correct. But anyway, by using the density shifts, by using the prior knowledge of the P wave parameters, and by using this relationship between S wave and P wave, we were able to determine all the scattering lengths for strontium. So the next slide that I want to show you is because after we published this paper, actually we got contacted by the, I don't know if you have seen the Big Bang theory. This is a very funny, I find it very funny series. And actually they wanted to do a highlight of our paper. They tried to actually show Sheldon coming actually to Gila to show that the SUN symmetry of the interaction. So this was supposed to appear, I mean, according to the scientists working on the Big Bang theory, it all began with Sheldon's participation in the Rila research team, hoping to confirm via direct observation the spin symmetry theory in quantum physics. Sheldon, used to working in the theoretical realm, found his colleagues alienating like Penny in season 1 to 3, the Big Bang theory. However, under the tutelage of Ana Maria Rey and Junge, Sheldon was learned how best to unify the two fields, resulting in the remarkable new finding. So it was so funny. I mean, at the end, in this series, this chapter never appeared. I mean, they never transmitted. But it was so interesting that it caused so much of attention, this determination of the SUN symmetry with these parameters. Yeah, okay. So I told you the older version of the clock, when they have 1D lattice, and Thomas was saying hot. But of course you don't want that. I mean, you want to have a clock that is quantum degenerate. So the new generation of optical lattice clocks at Gila now operate with actually quantum degenerate gases of strontium atoms. So they were able to evaporate the atoms and reach temperatures of T over Tf of the order of 0.1, low temperatures. Now these experiments operate, actually I'm going to remove the mask. Now they have shown that they can reach quantum coherences in this 3D lattice of 12 seconds. That is remarkable for, I mean, it's not the 100 seconds lifetime, but it still is 12 seconds. And we are trying to now explore new physics of SUN atoms in a 3D lattice. Now, this simplifies our task a lot because P-wave interactions disappear from the problem. If you go to quantum degeneracy, really P-wave interactions are completely suppressed. And then our task is trying to look at only SUN S-wave interactions. And when particles are in a lattice, actually the physics is reduced to what is called the Hobart model. So instead of having kinetic energy, now you have particles that can tunnel from one lattice side to the other. And this tunneling is set by a parameter J. They operate in the magic lattice, where actually all the nuclear spin and the ground and the excited state feel exactly the same potential. So even though I wrote alpha here, actually this is the same J for everything, for all the particles. Now we have a Fermi-Hobart model that we have the same type of interactions that I showed you before. We have, alpha can be E and G, and we have this density, these interactions between ground state atoms. Now, because they're SUN, what I don't, instead of writing, let's see, where is, here. So, before we get writing something as a sum over Ng N NGM. Yes, basically that's what the type of N is the nuclear spin. Yes, and we are going to sum over all different N's and all different N's. But then because of that, you can actually write this Hamiltonian as sum over total N. If you define total N, G is the sum of Ng over the all nuclear spins. Then you only need to have the Ng variable. So it's Ng, and this is Ng minus 1 because of, you can only have interactions when you have more than one atom in per lattice site. So you see that it looks very similar to bosons. That's the advantage of the SUN, that actually you start to have, and I will explain a little bit more the connections to bosons later. So you have the standard interactions, UGG or UEE. Now we have the direct term that is proportional to the number of atoms in the ground and the number of atoms in the excited state. And then as before, you now have exchange, and this exchange term generates flip-flops between the atoms. Like we explored this term and they measure this B exchange. But now we are going to sum over all M and all P. This is the nuclear spin M or P. We are going to sum over all these different configurations. So this is the Hobart model that governs the SUN Hobart Hamiltonian that governs the physics of these atoms. And these interaction parameters that are, instead of these four formulas that I had before for gradients and things like that, and particles in different motional harmonic oscillator states, everything is very simple because I'm going to wait for the Warner function, the orbital that characterizes the atoms in the lowest band. So everything becomes much more simpler when you are going to reduce the system to these much lower temperatures. So this is describe the Hobart model for these atoms. So now, these are the three types of interactions, and remember, the B exchange is the sum, the direct term is the sum, the exchange is the difference between the interaction parameters, and we have in generally this Hamiltonian that nevertheless is very complicated. But the first experiments that June started to do is try to use the clock. And actually in the clock, this is a 3D lattice. And in principle, he can prepare lattice sites with 2 atoms, with 3 atoms, with 4 atoms. And actually, he was able to spectroscopically resolve these different sites, these different states, because they have different interaction energy. So these have different interaction energy, that 3 and 2. So let's try to understand now in very simple terms what is the interaction energy when I have 2 atoms, or when I have 3 atoms, or when I have 4 atoms, taking advantage of the SUN interactions. So if I have 2 atoms, now in the clock, they started with atoms in everything in the ground state. They applied the clock laser to go from GG to EG. So we never were, the 2 photon transitions that go EG to this were forbidden, suppressed, also because this state is very lossy, so it never happened. So basically, the only states that we can populate is GG or EG, that's it, but we can have different nuclear spin configurations, yes? So if I have 2 atoms, then now I'm going to write, I'm sorry, this is confusing, but it's simpler. Up is E, down is G, and I'm going to add something with color because I have different colors of nuclear spin. So the Eg plus is going to have a plus between E and G, this term here, but it's going to have a singlet in the nuclear spins. Yes, we saw that. Now, same for the down-down, but it has interactions only in the ground state. And then I have UEG minus that have the minus here and requires a triplet in the nuclear spins. So this is, I call it SU2 singlet because it's only 2 particles, but it can have different flavors. Yes, yeah, the SU2, this S can be a MN minus NM, when M can be any of the flavors between minus 9/2 to 9/2. That's what I call it is SU2 singlet because I only have 2 atoms in my system. But now, if I'm going to have sites with 3 atoms, then things become a little bit richer, yes? So there is a state when I have fully symmetric function in the EG levels, yes? I only can have one excited state, but I can fully symmetrize or where this excited state is, or is in this atom, this atom, this atom is a fully symmetric state. And if this wave function is fully symmetric in the orbital degrees of freedom, I need to have a fully antisymmetric form state in the nuclear spin degree of freedom. So I call it this as SU3 singlet because I have 3 atoms, yes? So this singlet, same here, if I have all the atoms in the ground state, I have to have a fully antisymmetric state. You can see that it's easy to write in terms of fermionic operators because if I permute any of these 2, I get a minus sign because I have fermions. And then I have another state, now that is complicate my things, the way that I write because I cannot fully antisymmetrize when I have 1 E atom and 2 G atoms. I can never fully antisymmetrize because it's not possible for this configuration. So I have states that are partially antisymmetrized. Of course, the wave function has to be antisymmetric, but it is kind of, you can construct the states by trying to write a slather determinant of states that have, for example, up, down, down, up here, and this state in the ground state. This is one type of other states that can happen in my system, and same thing when I have the up down between the first 2 and this is ground. The important part is that because I have SUN interactions, then there is only going to be 3, the energy configuration for everything is in the ground state, 1 interaction energy when everything is fully symmetric, and these other configurations are going to have a slightly different energy but the same. So if I go to N atoms, I only going to have 3 different energies that are possible. So if I have GG atoms is N minus 1 divided by 2. You are familiar with this type of terms. If I have the fully symmetric state in the orbital and the fully antisymmetric state in the spin, I have something, it's not that obvious, but this is, there is going to be an UEG plus because it's fully symmetric, and this atom is interacting with, there are N minus 1 of this type of symmetrization, and then the remainder, and there is you have one pair that form EG, and the remaining N minus 1 atoms interact via ground state interactions. So this has this form. The important part is that there are only 3 different interaction parameters for system with N atoms. So if I have in a well with N atoms, I'm only going to measure 3 possible interactions. That's it. Now, that's what, this is an SUN singlet when I have different N flavors in my system. Actually, this state is what is called a W state. So these states are going to be highly entangled because of the fermionic statistics that I have to satisfy within a well. So now let's see what June measured in his clock. So when the reference was when you have only 1 atom. But now when he start, and this is, of course, one atom doesn't have any interaction shift, so this is going to, that's what I put it at 0, the tuning, because this is my reference. Now, when he had 2 atoms, he sees, and now, instead of having 3, I'm going to always subtract, for example, UUG plus minus UGG, because this is the energy that the clock can have. He starts with atoms in the ground state. He wants to excite one of it, for example, he wants to go from GG to EG plus G. So the energy difference is UEG plus minus UGG. Yes? So that's why we see only 2, because if I, so is this UEG plus and UEG minus. He see only 2 peaks. Now, if I'm going to have 3 atoms, he only see also only 2 peaks. If I have 4 atoms, he only see only 2 peaks, the plus and the minus. So it's fully confirming the SUN symmetry. Otherwise, I would have a soup of peaks. So now it's a very, very nice, simple verification of the SUN symmetry in the system. He was able to go up to 5 particles. There is a little bit of 3-body losses, but not too much, because I only, in strontium, in contrast to ytterbium, the orbital phase-back resonance is very far away, so we don't have any EG losses. All right, so everything looks great. So we have this. So now, in principle, because I have all the scattering lengths, or with these peaks, I can compute what is the scattering parameters too, in a much more simpler form. And actually, for 2 particles, as a form, he can change the lattice depth, and he can try to look at what is the slope of these interaction shifts. And with this, he was able to actually compare the scattering lengths that we extract by this messy one-dimensional clock that I have to have this complicated model with this very simple, nice Princeton 3D lattice model. And very nicely, we find that the agreement between what we computed and what they were measured was very nice. So our model was right. So that's good. Okay, but here is what they found. That's great. But this is what they found. Now we use the hover model that I wrote before. We use this hover model that I wrote in the Blackboard before. This Hamiltonian. We can compute everything for 2 particles, for 3 particles. It's very simple. We have the interaction parameters because we measure AG, the scattering length, so we can compute everything. And then we were thinking that we are going to have perfect agreement with what we measure to what they see in the clock. But no. The clock was so precise, the clock is very precise, and we will only agree with the 2-body parameters. But when we have 3 particles, it was not the same. When we have 4 particles, it was even bigger disagreement. When we have 5 particles, there were even larger disagreements. So we were puzzled by what was going on. We have all the scattering lengths right. We have the hover model right, we thought. But the point is that the clock was so precise that the conclusions we learned that now they were able to see multi-body interactions in the clock. So when you have 2 particles, it's okay, but when you have 3, 4 particles, you can see multi-body interactions.
So maybe it's a really stupid question, but on the slide before, on the right-hand side, one really sees that it doesn't fit, but on the left-hand side, so with the minus signs there.
Yes, I'm going to explain why is that. Yes, that was some of the surprising evidence that for the plus were much worse than for the minus. So they remember that there are 2 possibilities. For the fully symmetric, things were worse than for the ones that were partially antisymmetric. Yes, I'm going to explain you why is that. We're going to explain what is going on. So the point is that, nevertheless, we were not the first one to see these are effective multi-body interaction in the clock, but actually Emmanuel Bloch in 2010 was also seeing multi-body interactions in his bosonic experiment. And the idea is very simple. The idea is that if you remember that we are computing the interaction parameters by using Warnier orbitals, or their single particle eigenfunctions of the atoms, of a single atom. So the way when I wrote U, I was looking at something that was proportional to the scattering length, like the wave function to the 4. Yes, that's what I was computing, and this is a single particle orbital. The point is that these single particle orbitals are not exactly correct. Actually, when I have 2 particles, I have different single particle orbital than when I have 3 particles, that what 4 particles. And actually, what is going on is that the Hobart model that assumes that you have the same Warnier orbitals to determine the interaction parameters is incorrect. Mm-hmm. And the way that Emmanuel explored this incorrect behavior was, well, maybe I'm going to, because I'm starting to go, it's 7 p.m., so maybe I'm going to tell you the story, and tomorrow we are going to go into the details. The basic idea is what he did to prove and show that were effective multi-body interactions is that he says, well, let me start by preparing a superfluid. A superfluid is when in each lattice site I can have a system with different number of particles, like a coherent state. So if he has bosons, and then he says, well, imagine that that's the schematic cartoon here. In each lattice site, I can have a superposition of no atoms, 1 atom, 2 atoms, 3 atoms, because, of course, the total number of atoms is conserved, but in a given lattice site, some experiments, sometimes I have 1, sometimes I have 2, sometimes I have what is called number fluctuations. So I prepare a system where in each lattice site, you have n atoms with some coefficient. This is my initial state. And then I'm going to quench the lattice to be very deep. There is no tunneling. So now the interaction Hamiltonian is going to be coming from the interaction term. That's it. There is no tunneling. So it's going to be U n minus 1 divided by 2. These are the interaction energies. Now notice n is an integer. So each of these states with n atoms is going to acquire a phase because they have different energy. But notice that that n is an integer. So if I have times that are multiple values of 2 pi, is u times t is 2 pi with some, for example, is 2 pi, then all of them are going to have the same phase because n is an integer. So when what he did is that he prepared the system in the mode insulator, and then he quenched the system and tried to measure in the momentum by time of flight the expectation value of the operator A that is associated with the number of parts, the coherences, but is associated. You can compute this A is the is the operator that destroys a particle in a given site. So he can extract this by letting the particles expand. And you can compute from this simple formula that what he should see is what is called collapses and revivals. But in principle, these collapses and revivals should, at multiples, when ut is multiple of 2 pi, they have to revive all the time. That's what he expected if we have a model that is like this. So this was the theory, what he was expecting. We have collapses and revivals of this operator. And what he saw, nevertheless, is something very different. This is scrambling of the phases. So with that, this is what he found is that these collapses, this lack of perfect collapses and revivals was generated by the effective multi-body interactions in his system. And it's not that there are genuine multi-body interactions, but as going to explain, there are the fact that this Warnier orbital has to include, it's going to broaden as I have more and more atoms, but this is can be recasted as a multi-body interactions. So next time, what I'm going to derive is a Hamiltonian that accounts for these multibody interactions. And with that, by accounting for the multibody interactions, I can show you that we can perfectly reproduce the interaction, these peaks that he measured in the clock. So the clock was so precise that he can detect even these tiny effects. So let's start with that tomorrow. And I'm also going to tell you a little bit more about spin orbit coupling, a little bit with interactions in the clock. Any questions? I mean, it's a lot. I imagine that you are exhausted, completely fatigued with all the lectures. But I hope that you got a little bit of what I was saying. And I will, of course, the slides will be available. I should send you the slides tonight.
Put them on the website.
On the website, so you can follow. I mean, I know that these were very heavy with formulas, complicated formulas, but hopefully you got the idea of what I was telling you, that collisions are very important in the clock, but at the same time, the clock is a fantastic tool to measure these many body effects. Now you can enjoy and have.